All right, welcome back, Algebrists. Today is Tuesday. I should have changed that. September 30th. Uh, Anybody start looking at Halloween costumes yet? Do you guys do Halloween costumes still? Cool. What are you guys going with? Should we save it as a brain break? Let's save this as our brain break because that's a natural discussion to have. All right, today we are going to start and go way longer than your book suggests, section 2.3. And we are going to be looking at factoring quadratics. Factoring quadratics. Now, for this, you guys, I imagine, recall that factoring was a huge part of Algebra 1. Pretty much from January to May, you factor stuff pretty consistently in an Algebra 1 course. Okay. I think that me and Russell and me and Jarvis all approach this pretty similarly. But if there's words that I use that are different than the ones that you recall, please call me out. I can switch whatever I refer to it as. Couple random questions. Have you guys ever used physical objects to help you factor? Like tiles to make sense of them, maybe an area model? So that might seem familiar to some of you. I'll dig through my closet if we need to, and I have like physical objects that can help us factor, but there's better ways. Okay, so right off the bat, we have two objectives. We want to be able to write something in the factored form in order to solve an equation. We'll get there. But we're also going to use this to knock out our quadratic inequalities at the same time, which they feel like they're wildly different problems. They're not. Okay, so here we go. Our immediate topic is, what does it mean to factor? So I'm going to call this factoring. And let's just dive in. What is factoring? Anybody have a good explanation for what it is that we're doing? Okay, we're going to do a slight example. You guys don't have to write it down. If you want to write it in your margin, you can. Factoring quadratics is a big problem. Okay, you guys have done a ton of factoring, but maybe, I know you've done a ton of factoring with quadratics, but I'm going to do something over here. Again, totally optional if you want to write it down, because we're going to do factoring that you see in like 6th grade. What's your favorite number, Naomi? 4, and yours, Amy? And Mark?
2.
So 432, love it. I want us to factor this number. And we want to make sense of what's actually going on here. Do you guys know of any numbers that go into 432?
32.
So 32 goes in?
1.
I don't think 32 does.
I thought it was just
1 definitely does, but I'm going to be more specific. A meaningful number. 1's not meaningful. That came off as rude. 2 does. 2 does. Weird. 2. So, you guys have probably built trees before. 2 times what? 216. Okay. Can I break down 2 any further? How? So, is 1 a meaningful thing to write? Ever? Pretty much never, especially with factoring. If we can't break it down any further, there's a word for this one. Prime. This cannot be factored any further. It is a prime number at this point. 2 is the smallest prime number. Cool. Does 216 break down?
Yeah.
Any what?
2.
So 2 times 108. Once again, I see that my 2 is prime. Now, when you guys did your factor trees, you probably didn't do this. I'm going to let this one keep coming along. Anytime that I have a prime number, it's going to keep coming along so I don't forget it. Okay. These 2's are both prime. Can't break them down further. What about 108? Sorry, I forgot the 8. Does that break down further? 2 times 54? Okay, so notice I now have 2 times 2 times 2 times 54. And let's go one step further. 54? So we could do 2 times 27. Is there a bigger thing? 9 times 6? 9 times 6. Notice, and you don't have to do the number trees like this every time. I just want to make sure I don't lose them. Okay, all these 2's are still prime. Does 9 break down further?
Yeah.
How? 3 times 3 and 6? 2 times 3. Can I break down any of these last numbers down here anymore? Okay, so right now I would argue that I have what is called the prime factorization of the number 432. We have broken it down into all of its smaller pieces whose product is 432 in the end. Product meaning what? Multiplication. So if we wanted to write this out, and I know this is kind of ugly, but let's knock this out, and I just want to write this number completely factored. How many 2's did we get? I could write 2 times 2 times 2 times 2. Is there an easier way? 2 to the 4th. So all my 2's are knocked out. Any other factors? 3, and there's 3 of them. This is the prime factorization of the number 432. Now, this number tree probably looks a little bit different than the ones that you've done. You likely didn't draw your branches going all the way down. Does this seem okay, though? Now, you could likely do it. You might pick different numbers, and that's completely fine. But as we go through, we have just given a factorization. Do you guys have any reason in your real life to care about numbers and factoring? So I disagree with you. Follow-up question, doesn't seem related. Anybody ever type their credit card information on the internet? Or somebody else's credit card information on the internet? Definitely. If you've ever ordered anything off of Amazon or any website ever, or paid for something on the internet ever, you care about this whether you know it or not. If I send my credit card information out over the internet and somebody's watching and they intercept that communication, they get my number, right? And that would suck. If you go to a website, how do you know if you're like able to trust that website to handle your credit card information and your private data? The cookies. What do you mean? Okay, so here's a website that I know can take money. How do I read the cookies? So first thing, cookies are there not to keep track of like your personal information. They're there to keep track of which IP visited this website so that we know to advertise whatever it is to you. So beyond that, it goes crazier and deeper because if somehow the internet and whoever's advertisers, they know that Mark often texts somebody else because he's allowed them to access that information. Maybe you do, maybe you don't. If Mark searches something and he starts getting ads for it, that makes sense. If Talia starts getting ads for it, it seems like magic, right? It's not really magic because they know, the advertisers, they don't know who they are directly, but they know that these two numbers interact regularly. And if Mark is looking for something and he interacts with this other number often, maybe that person is also interested in that, right? Friends are interested in the same thing. Google might be listening to you, just so you know. Your Google, your Siri, it is listening all the time. They say it's not, but I think it is. But the advertising stuff isn't really a big secret. They share all that information. When you accept cookies, you're getting personalized ads. Now, if I go to this and I want to view the certificate for this, so they have cookies, so they're going to keep track of stuff. So if I search for bread knives, they're probably going to advertise a bunch of bread-related products to me. That's what cookies do. This is where it's more interesting. They see this certificate is valid. When we look at this, this is the schools one. Up here, here's our school. And then if you go to a website and you check and you want to know, gosh, should I really type my credit card information? This is what you're looking for. SHA 256. What this is it's a way to encrypt data. Now, we are not in a computer science class, so we're not going to go hardcore into that. But the entire foundation of can we keep your information secure relies on whether or not a big, like hundreds and hundreds of digits number is a prime number or not. Factoring even numbers is a challenge if you get really big, and that's a good thing because it allows us to keep all of our private information safe online. Okay, to my knowledge, nobody has broken SHA 256 yet. When it happens, and it will happen eventually, especially with quantum computing and stuff, SHA 512 will show up or whatever. Don't know if it will really mean a whole lot with quantum stuff. But you do and you should care at least a little bit about factoring if you don't want to have to like protect your identity all the time. Okay, the cool thing is that we don't have to factor digits and numbers that are hundreds of digits long. We get to just knock out factoring. So back at this, sorry for the little sideways tangent, but hopefully that's relatable. Okay, factoring is simply breaking. Now it could be a number or an expression. We're going to say an expression. And typically they'll be functions, but not always. Breaking an expression down into the prime pieces whose product is the expression. Okay. Breaking something down into the prime pieces whose product is that same expression. Now, when we go through here, there are so many different uses within the realms of algebra to where we might care about factoring. just to motivate a little tiny bit. If we have a graph, if we have a quadratic function, do you guys love graphing? It's okay, I hope. It's not terrible for you right now. But can we agree that if we could solve stuff without factoring, that would be better? Or sorry, without graphing. Like, if we don't have to graph, that'd be convenient. This is our route through it. What we use these primarily for is we care a lot about very specific key features of quadratic functions. I care about where the vertex is, oftentimes. I also care about where it crosses the x-axis, the zeros, the roots, the intercepts. Those are a fundamental thing that mean a lot of different things depending on the context. Our goal with factoring and the whole justification behind it is it lets us solve equations. And it lets us solve equations in an efficient and good way that otherwise maybe we couldn't do. All right. So for this, the way that I typically teach this, in Algebra 1, when you guys go through it, you learn, like, here's one method in one section. And then the next section would be a new method. And you put like 4 or 5 sections together over the course of a chapter. You likely don't remember all of it. And in fact, I know you don't remember all of it. That's okay. I'm going to give us the entire roadmap, what I do every single time with factoring. It'll get bigger throughout the year, but I'm just going to lay it all out there right now. And then we'll do examples of every single type of these. Sound good? Okay. So right off the bat, we're just going to go ahead and have our roadmap. And you don't have to call it roadmap. This is really just a series of steps, but I always think of it as a map for whatever reason, a flow chart, if you will. Okay. Very first thing, every single time to factor something, I would run through these steps every time. Step 1, we're going to check to see if there's something that goes into both terms. The greatest thing that goes into both terms. Anybody recall what we're going to call that? The greatest common factor. If you don't want to write these 3 words, greatest common factor, is there a convenient shorthand that every math teacher will use? GCF. Okay. I'm going to switch colors on each of these just so I can organize it here. When we get through all of this, something that I'm willing to do, if you can show me that you've taken notes and you just want nicer notes, I can print these. Like, I can print my notes any day that I want. I will print them for you in color if you can show me that you have good notes and you want them more nicely organized. Cool. All right. Always GCF. There's our first thing. Okay. From here, once we have checked and whether there is or is not a greatest common factor, we're going to check to see how many terms it has. It's possible that it only has 2. And what's the word for 2? Like a 2 cycle? That doesn't sound right. A bicycle, right? So we're going to check for, is it a binomial? Is it a binomial? Okay. For our binomial stuff, if it is, right now we only have one option. There's more out there, but as a follow-up on 2, we're going to check, is it a difference of 2 squares? A difference of 2 squares. Now, you will likely never see me write all of those out again. I just refer to it as a difference of squares. But as we look at this, first thing, GCF, sounded familiar? Okay, difference of squares, does that sound familiar? Okay, it's all right if it does, it's okay if it doesn't. There are 2 more when we rebuild this later. There's 2 more things that are going to go right here. We can redo it later, I'm fine with that. Okay, once we've gone through whether it was or wasn't a binomial, we're on step 3. If it doesn't have 2 terms, how many might it have? 3. So instead of a binomial, I might ask, is it a what? Trinomial. Is it a trinomial? So it's nice because 2 is binomial, 3 is trinomial. Okay. If it's a trinomial, there are a variety of techniques that we go with. I know the order that I always do them in. It is not the perfect order, just so you know. It's just the way when I teach it, I say these are the things that we check. If you want to move this order around a little bit, I'm fine with it. But here we go. Step 1. Is it a perfect square? Perfect square trinomials we have already factored. You weren't aware of it. Maybe I'm wrong because I'm confusing classes, but I'm pretty sure I know we've seen them in this class this year. Okay, if it's not a perfect square, my next step would be to check, does it have a leading coefficient? Which I use the shorthand LC for this, but I'll write it out this time. Does it have a leading coefficient, or LC, equal to 1? Can somebody tell me what a coefficient is, or specifically a leading coefficient? So kind of. It's a number. The coefficient part is a number. In a quadratic, what's the biggest power of x that we're going to see? So we're not going to see an x cubed in a quadratic, but we will see an x squared. Now, if we just check the bell ringer real quick, we'll go back to it. And each of these, here's an x squared, right? What's the number in front of it? So that's the variable. What's the number that I don't write, but it's actually here? It's a 1x squared. The leading coefficient's a 1. What's the leading coefficient here? A 1, because, again, it is a 1x squared. What about on this one? D. 3, because it's 3x squared. That's my leading coefficient. Okay. While we're here, leading coefficient 1, awesome. We will go ahead and use a shortcut, and I'll just put that underneath this. And I know it gets nested, but there's a lot to it. There's a shortcut that I'm going to recommend if and only if the leading coefficient is 1. All right. If it's not 1, leading coefficient is not equal to 1, we are going to group it. Group it. Okay. The last step for today, at least, if the leading coefficient is not 1 and we can't group it, then our very, very last option, and this is more so with solving, but it's everybody's favorite thing, the quadratic formula. Okay. While we go through here, we're going to give you like 30 seconds. Which words and which things here do you recognize from Algebra 1? Which things have you never seen or you don't recall whatsoever? 30 seconds chat with your neighbors. I want to get a feel for where memory stuff is. Do you remember the word? Do you remember what it means? So forth and so on. The other one, but like grouping, no. Okay, so that helps. Perfect squares. Okay. All right. Any words up there? Anybody does not recognize even a little bit? Like it seems like the first time you've ever seen the word. What? Does anything that we have written up there feel like this is the very first time you've ever seen that word? Yeah. Which one? Or ones? Squares. The difference of squares? Anybody else agree with that? Never learned perfect squares. I think you do remember or you don't? I've never learned it. Okay. We'll see. I don't know that you have or haven't. I'm trying to remember back to Algebra 1. We'll learn it now, and I'm cool with that. Okay. So maybe the difference of squares. Let's jump in. We're going to build complexity up. Today is nothing but example problems. Cool. All right. Now, we will generalize these rules, and I'll help you do it, but let's go ahead and start at level 1. I wish I had written this on the whiteboard so I could keep it up. Cool. All right. To begin with, here we go. Let's factor, and I'm going to factor using, what's the first thing on the list? Boom. Let's factor with greatest common factors. Okay. Greatest common factors are always the first thing that I would check, with like one very specific exception, but we'll deal with it. All right. So all that we're going to do is break these things down into the smaller pieces. So let's get a bunch of examples. Our first one, let's say we're given some expression that looks like x squared, you know what, x cubed plus 2x squared. Okay. Now, we need to agree on the language that we use to refer to these things. If I say how many x's are up there, there's a bunch of different answers. I'm going to make a claim before we just shout them out. I'm going to make the claim that there are 0 x's. Do you agree with me? Okay, a lot of you probably don't, because you obviously look up and you see the letter x up there multiple times. Okay, here's where we need to be really clear. If I want to ask about just the x terms, that's different than me asking about the x squareds and the x cubes. So how many x cubes do we have written up there? X cubed was written once. Now, x squared, it's only written once, but I see there's a coefficient on it. That's fine. Are there any x to the first powers, or just x's?
No.
So we all agree there's no x's. Okay, so if I wanted to break this down, and if you need to do this at first, you can. I would not recommend it. But what does x cubed actually mean? I would skip this first line if I were you. This is x times x times x plus 2 times x times x. Everybody okay with saying that's what this really means? Can you tell me when we look at this, out of each term, I have a ton of x's, right? How many x's could you take out of both of them? It has to be the same number. Do we take 1 from each? 2. We could also take 2 from each though, right? Okay, if I took out an x times x, I've taken out the greatest common factor. I've written them all out. I can see this is the most stuff that they have in common. Alternatively, if we can not write this, we'll save a ton of time. Do you guys agree that x cubed has an x squared in it?
Yes.
It's x squared times x. Okay, there are 2 ways that we can look at this, and it just takes practice to get good at it. Okay, I'm going to begin, instead of showing all of that factorization, factoring feels what color to you?
Red.
Okay, we'll go red for now. All right, do we all agree that there's an x squared in both of these? Even though this one's an x cubed, there's really an x squared. Okay, here's the part where we have 2 ways of thinking, and I don't care which one you use, I know which one that I use. When I look at this problem, I know that whatever I write in here, if I FOIL it back out or distribute, I better wind up with what I had originally. Okay, I think, and this is my thought process, x squared times what gets me x cubed? That's how I think about it. X squared times, oh, it's x. Okay, does everybody else think about it similarly? If you struggle with that part, the other side of it, if you're comfortable with exponents, we can think about it a little bit differently. If you took x cubed and divided by x squared, what would remain? And that's a harder question, maybe. But if you don't want to just say, oh, what would I need? If I took out an x squared, and I wrote it all out, this would be x, 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 and this would be over x, x. What falls out? What divides out of this thing? The x's, right? So what am I left with? 1x. Whether you want to just imagine you're multiplying or you want to think about the division part of it, doesn't matter. We're going to get the same answer. So check it. We have x squared, and then we have an x left inside. What if I took an x squared out of this 2x squared? What would remain? Just a 2. We're done. This is the greatest common factor that's been completed. Now, to check, and checking can be really tedious, this is entirely up to you, but I'm just going to redistribute to check. You do not have to write it down. If I redistributed, what's x squared times x? That's x cubed, and x squared times 2? 2x. Is that what we started with? I'm convinced that we have the right factorization. Okay, after we've done this problem, does GCF seem a little bit more familiar? Okay, we're going to do one more. I'm going to give you guys a slightly harder looking one, but that's it. It's just slightly harder looking. All right, on B, I want x squared y cubed plus xy squared plus xy. I want you guys to factor out the biggest thing that goes into all 3 of these. Super important. Sleepy. That's okay. Do you remember? Exactly the same. All right. So coming together. I see it's going okay. Some of you guys are using my advice to do the long way. I would strongly encourage. I have no issue if we write these terms a little differently first, but we want to move past it because otherwise one problem is going to take forever. Okay. This first term, if we wrote it, is xx y. X squared y cubed. Plus x, what's the square connected to in this middle one? So y plus xy. I would not recommend doing it this way on a regular basis, but if you're trying to refresh it, absolutely, this works. What does each one of these three have? So they all have an x, and I'm going to cross it out just as I'm doing that. And the second that I do that, I'm going to say, all right, here's my factorization. There's an x that came out. Anything else that comes out of all three of them? A y term, there, and there. Just one, right? So I factored out an xy. Okay, what's left in here if I take one of the x's out? So you say the 2, but remember that's x times x, Kennedy. I see where that happens. But if I take one of the x's out, and I can see it here, what remains? It's just one x, right? And how many y's remained? So how would I write 2 y's? Y times y. Is it 2y or is it y squared? Y squared. Now, if you have to write these out, again, I want to stress it's okay, but I want us to start trying to make that generalization immediately on how we can avoid this. Forget about this picture for now, and I'll just do this so we can't look at it. If I took the x out or divided by x, either way you think about it, the x is gone, right? And if I took one of the y's out because it was y times y, what's the only thing left on that middle term? Just a y. To verify, I will just undo my scribbles. If I took out an x and a y, I'm left with just a y. Exactly what you guys told me. Plus, this last one's the trickiest. If you took an x and a y out, you're going to be tempted to say there's nothing left. But if we treat it like it's division, there was a 1 because we just divided it out or factored it out. Okay, looking at this one, noticeably uglier, but was the approach really any different? No. Now, I'm going to check this real quick. If I did this, I would get x squared y cubed, which is what I'm expecting. Here, I would get an x y squared. That's what I had. And this last one is plus xy. It's what I had. Okay. These problems. This one's uglier than the vast majority of them that we'll see. Should we do one more purely of this form, or should we jump and add a GCF into our next step 2? One more. All right. Ugly or nice? Okay, so it's going to be like middle ground. Not this ugly, but uglier than this. So here we go. I want 3x squared plus 6x plus 9. I want you to factor out the greatest common factor and only the greatest common factor right now.
We don't need to write the little equation inside. We just do the triangle.
So are you talking about the purple stuff that I did?
The red stuff, we don't need to do that.
So the red is the answer. So even if we use the purple to get the red, I'm okay with that.
Oh.
Do you not connect? Are you okay? Awesome. Yep. I would like to not write the purple eventually, but for today I'm okay with that. Yes.
I have 3 times x squared plus 2x plus 3 times x squared plus 1. Plus 3 times. Yeah.
So I think you do the whole thing time. Instead of 6, how do you make it?
Oh wait, it's 3x.
3x times 2
It's just 3 more.
is 6x the same as being, you have x times 6,
I
right?
know what I
Did
did.
you write it 2 times 3 here instead of 6?
Yeah, so 3x plus.
You should, and you'll see why in a second. I'll do the same thing like that.
X squared plus 2x plus 3.
So that's x times 2 times 3, and how about 9?
Yeah.
With the prime factors. Good. Good. So now the question is, why do they keep that? What do they all have in common?
6x.
Oh.
You have factored it to 2, 3x.
All right, checking it out. This one looks kind of weird. If you are using the purple, I'll keep doing it for now. The next ones we won't, just so you're aware. Okay, So check it out. This one, if we write it as its prime factors, it's 3 times x. Everybody agree with that? Plus, this one's going to feel weird. Instead of 6 times x, Kyle, what am I going to write? 2 times 3 times x. Now, I'm doing this only because I need to identify if there's prime factors that they all have. Now, I don't know what I do know what the prime factors of 6 are. If you can see that a 3 is going to come out in the end without doing this, I would encourage do it. But I'm going to write these with all the prime factors so I can see if there's anything that's the same. What's the prime factors of 9? 3 times 3. When I write it in this way, it becomes much more clear if you're struggling to see it. What goes into all 3 of these? What do they all have? So they all have a 3, so I'll take a 3 out. Do they all have an x? No, the last term doesn't. So can I take an x out of it if it doesn't have one? Nope. There's nothing else that these have in common, which means inside, instead of xx, what did we have? X squared. And inside this next one, what do we have? 2x. And last, plus a 3. We are using GCF over and over and over. Cool with that? All right. We ready to bump it up? Sweet. Binomials, I used nothing but red, so we're going to bump it up a little bit. So example, in binomials. Okay, I'm going to give us the general form right off the bat. And I'll show you the thought process that I use. I'm going to, before I say example A or B, we're just going to sneak this in here. A binomial must be of the form, if we're looking for a difference of squares. First of all, what does difference mean? Say it again. Subtraction. And what's a square? Like it's a shape, but what about with numbers? What's a square? So something by itself. Is 9 a square number? Yeah, because it's 3 by 3, right? Is 16 a square number? 25, 36, 49? All of those are our square numbers. When we look at this, it's going to look ugly here. What we're ultimately looking for is something of the form a squared minus b squared. Now, when we look at this, we can evaluate and we can derive and see where this comes from once we get a little nice grouping stuff going on. This is what we're after. Here we go. For our first one, starting off easy, and this should be red because that's what it is in my notes up above. On A, we're going to factor the following. We'll start super easy. X squared minus 25. Now, the second that we have a binomial, we should be immediately thinking about the difference of squares. Do I have a binomial? Is it a difference between them? You say no, but is that minus? I think so, right? Okay, so check it out. Can you guys tell me the square root of each of these? Do you know the square root of x squared? What times what? What times itself gives me x squared? X times x. Yeah, I think we do. How about 25? 5. Are these both squares? Okay, so when we factor this, and I'll write something up above here in just a second, we'll generalize this rule. If you can look at this thing and tell me that this is an x and this is a 5, you've done the hard part. That's the hardest part. Check to see if they're both squares. If you can take a square root, it factors super quickly, super nicely. And I'll switch here. What was that first square root? And the other one? So whether the order doesn't matter, but notice, square root of the first and square root of the second, here's a minus. And if I do that again with a plus, I just want to see what happens. I'm going to claim that these are the same expression. And you might not see it right away, but let's verify that. Help me FOIL some stuff out real quick. If I want to check, when I do this distribution, I better get this. Like that's how I can always check. If we FOIL, what's x times x? Okay, so I have an x squared. And this is just a check. You don't have to write this down. I just want to convince you. There's my x squared. What's this one going to give me? Plus 5x. How about the inside? Minus 5x. And this last one? That looks very different than what we started with. Oh, 5 and negative 5x, they zero each other out. They're gone. Do we have exactly what we started with? X squared plus a negative 25 or x squared minus 25? We're done. Okay, for this, it means that if we wanted to, and I have a closed parenthesis, but that's okay. If we wanted to factor this one, do you know the square root of a squared? Do you know the square root of b squared? Is it a difference? This one right here it is, right? So it means I always do the minus first. I don't know why. It doesn't matter which one we do first. A minus b times a plus b. Every difference of squares ever will factor like this. Okay, let's knock out another one. It looks like we'll just finish up with some difference of squares. One more together. Do you want to try one on your own? Okay, so check it out. I'm going to throw you a curveball. 2x squared minus 18. Before you get going with it, I want us to refer back to that list. Anytime that we're factoring, we have a whole flow chart, a roadmap that we run through. Very first thing we always check is what? Okay, Sonny's got it, but I want everybody to have it. And there's not many times I do this, but I want everybody to tell me the answer. What's always the first thing we check? Okay, so that was a little higher. One more time. We're just going to do GCF, okay, so we don't have to do anything. What's the first thing we always check with factoring? GCF. Awesome, that was closer. Still not 100, but I'm okay with that. Do you think there might be a greatest common factor here and a reason I'm stressing it? Yeah. Cool. Factor out the greatest common factor first, and then look and see, do I still have a difference of squares? I'm coming around to be nosy, but I'm also coming around to make sure that I can help if you struggle. Make sure you're doing it. So, love it. Check it out. If we look at just the numbers, and I think that we can get by this easily, or like, it's okay to do this, but it's even try that. Do you know any numbers that goes into 2 issues? Sorry, 2 and 18. So what I want you to do is, you see that, and we're just gonna try this right off the bat. You have equals, because we're moving on, so equals right here. Okay, good. Yep, I'm good with that. Let's put parentheses. If you divided this by 2, what would you do? If you took the 2 over 2 is 1. So there's not right? So right here. And are you okay with division, or do you? Okay. So when I say factor out of 2, it's no different than me saying, write this out here and divide it by 2. What is this one factor? Okay, minus 9. So, yep, so now we factor. Okay, now let's look at this. Say pi x. That just means pi is how many? 2. What is it? So, almost. What's what times the cell? What type of stuff is it?
Where it's like,
Check it out. I want you to add those every time.
write it out all of them.
A minus B.
Otherwise we get 9 points.
Oh, I would write all the.
Where A is. Next line.
I know I had one. I'll do algebra again.
Good, so X minus 3, and then one more. You're close. So you did do GCF. All right, so coming together, first thing, your input. I can't always adjust, especially with 25 to 6 to 4, however many people are in here today. Am I going painfully slow, or is it feeling okay? I can go a little faster? Okay, I'm fine with that. If there is going to be a division, because somebody's going to say I'm going too fast, we'll try to balance it. I will make sure to give more examples. But let's finish this one, and we're not going to have homework. First thing, what comes out? A 2. When I take the 2 out, is everybody left with x squared minus 9? Okay, I'm not going to lose the 2. It's going to come along for the ride. As I look at this new piece that I just made, the x squared minus 9, is there any more GCF to deal with? You say yes. What goes into x squared and 9 though? Okay, so nothing else comes out, right? Is it a binomial? you say, gosh, I feel like I'm just targeting you, Angel, and I love that you're talking, but I'm not trying to argue against you over and over. It's just inside the parentheses binomial.
Oh, yeah.
There's two terms. Is it a difference? Do you know the square root of x squared and 9? So check it out, just using this formula. And we'll write this and we'll piece out. My 2 does not fall out. What's the square root of this? Minus what's the square root of that? And the other factor always is just the same but with a plus sign. We're done. Cool. We will continue tomorrow.
You also have the 2 in with the first parentheses, plus 2x minus 3, and then.
You could. It would be weird to do that. You can only have it in one of them. You could. It wouldn't be 2x minus 3. It'd be 2x minus 6 because you'd have to distribute. Okay. Don't do that. Cool. All right.